What we've got here is a nice cubic equation, and we know certain things about cubic equations which are going to help us in this particular question. So quick sketch always goes well. You notice in my equation that the coefficient of the x cubed is positive, so I know that all positive cubic equations look like that. The only thing I don't know is where they are, and that's what this question is asking me to do. So if we're interested in stationary points, those are the points at which the gradient is not changing. It is neither positive nor negative, and seeing as it's neither positive or negative, it follows that the gradient, and we're in a Cartesian format here, so therefore gradient is given by dy by dx, and dy by dx has got to be equal to 0. So clearly what I need to do in this particular case is I need to start with my cubic equation. So y equals x cubed minus 3x squared, and I need to differentiate it. So most people apply Wallace's rule at this stage. Interesting person, Wallace. He was the king's cryptographer. He was their spy master, and he was good at making codes. So Wallace's rule is multiply by the power, bring the power down by 1. And we'll talk a little bit further about why that's the case in a minute. And I can do it for each term independently, so multiply by 3, bring the power down by 1 gives me 3x squared for the x cubed term, and minus 6x for the quadratic term. Now, what I've got to do, and I've got to do it explicitly, is I've got to put that equal to 0. It's important that you do this step because you've got to show that somewhere you're linking the fact that stationary points have a gradient function of 0, and your gradient function for this particular curve is 3x squared minus 6x. Mathematicians like curves because the gradients are always changing. With a quadratic like this one, easiest thing to do is to pull out a common factor rather than use formulae or factorization. Pull out a common factor, that's probably the best way of going about it, which gives me that either 3x equals 0, which implies that x equals 0, or x minus 2 equals 0, which gives me that x is equal to 2. Those are the x coordinates of my turning points. Relatively easy case here of if x equals 0, y is equal to 0, so therefore I've got a turning point at 0, 0, which is nice, means I don't have an intercept on this particular graph. And my other one, x equals 2, y is equal to 2 cubed minus 3 times 2 squared. 2 cubed is 8, 2 squared is 4, times 3 is 12, and 8 take away 12 is minus 4. So my other turning point is at 2 minus 4. It now means that I've got to decide which one's a max and which one's a min, and this is where my shape came in. Because I know that positive cubic graphs always start in the negative quadrant, because a negative number cubed gives you a negative number, and a positive number cubed gives you a positive number. I can actually tell that the 0, 0 point is my maximum point and the 2 minus 4 is my minimum point, but because we're under exam conditions, we do need to prove it, and typically we know there's a number of different ways of doing this. One, I could inspect the gradient either side of those points, which would involve me in 4 pieces of mathematics, or more traditionally we use a second differential, d2y dx squared We'll discuss in a few minutes about why that's the case. So I differentiate it again applying Wallace's rule. Differential of 3x squared would give me 6x minus 6, and when x equals 0, d2y dx squared is minus 6, and when x is equal to 2, d2y dx squared is equal to 6 times 2 is 12, take away 6, which clearly is going to be equal to 6. You notice a certain amount of symmetry there. Now there's an implication in here that if my second differential is minus 6, i.e. it's negative, I know that I have a local maximum point. So therefore 0, 0, which is the point I found, is a max. And here my implication is that if it's positive, then my other point, 2 minus 4, is a min. Now that's a little bit counterintuitive, but if you think back to the standard curves, nice easiest curve to work with are parabolics. And we've got happy parabola, and that's of the form ax squared, where a is greater than 0. And this is a sad parabola, a is less than 0. Now, because these are of the form ax squared, okay, if I differentiate it, I'll get 2ax, differentiate it again, I'll get 2a. And clearly, if a is less than 0, d2y dx squared is less than 0. That's clearly a maximum point. And if a is greater than 0, d2y dx squared, and I'm not going to write that in because I actually haven't got enough space, is going to be greater than 0. And that's a minimum point, and we know that because of the shapes. So that would be sufficient. Obviously, we'd need to think about why the differential works the way it does. Draw a sketch of C, clearly indicating the stationary points. Now you've got to actually identify those points there, and the points, now normally I'd say look at that, there's a plural going on here, so there's more than one point. A little bit sneaky. Sketches don't have to be particularly good, but they do have to have some indication of size. So I'm interested in, I've got a local max at 0, 0. I've got a local min at 2 minus 4. And the only way that's going to work is if it cuts the point one more time. So I need to know this point here. Now clearly this is my trusty x-axis, and we know that the trusty x-axis is the line y equals 0. So therefore I need to find the root. Now I could have done that straight off, but the question wasn't asking for it. My function was y equals x cubed minus 3x squared. And if I pull out my common factors, x squared, x minus 3, and I let y equal 0, x squared, x minus 3 equals 0. Okay, I got that x squared is equal to 0, which clearly implies that x equals 0 twice, which does imply a turning point or a stationary value. Okay, so there's an implication here that I've got either a min or a max. And I could see that straight away from reading the question. Or x minus 3 equals 0, which gives me x equals 3. So clearly I've already dealt with my x equals 0 bit because it's there on my diagram. Here's my other one, x equals 3. And I've sorted my question. It's actually difficult to draw smooth curves on here. Obviously on a piece of paper I could draw a much better curve than that one. But in general, if you're looking for a sketch, you should identify roots, which is where it hits the x-axis, intercepts, where it hits the y-axis, and the positions of any stationary points. And you notice I've done that by just showing the basic shape and the coordinates at which they occur. Now, without doing integration, and certainly I'm not going to do integration for 1 mark, we know that we've just sketched the curve, and the curve looks like this. It's not perfect, but you notice here that if you'd read parts of the question, it actually tells you where your root was. It's always good to read through a full question. So we know that the area under a curve is given by the integration. And that's all to do with the fact that we can split the curve up into little strands, and each of those, or little rectangles, each of those have got a thickness. Usually we use delta x, and each of them have a length, which in this particular case is y, and therefore what we've got is that the integral of the area that we're interested in is the sum of all the y times delta x's, because they're rectangles, and what we're interested in is if delta x tends to 0, that summation symbol I use actually becomes the Leibniz notation, which is the integration notation, and it's actually a German letter S for sum, and that simply becomes y dx. And I haven't put limits in here, but that's where the limits come from. So therefore, area under or contained between curves and lines, typically in this case because of the x-axis, because we're using y lengths, but it could go the other way, will be given by integration. So if we look at the bit we're interested in between 0 and 3, we've got this section here. And because we tend to be biased and consider things that go up to be positive and get things that go down to be negative, then clearly because it's below the axis, it's going to be negative. So therefore I can claim that the integral between 3 and 0, x cubed minus 3x squared with respect to x, is going to be less than 0 because it's below the axis. And I would normally write that as a sentence, but in this particular case I'm not going to.